was tried Sonnet 4.5, or sorry, Haiku 4.5. Small model.
How is it? Is it as good as they say?
I think it's fast. It's a pretty big thing. Speed plays a lot. Like recently, I've been trying Codex CLI a lot more, and frankly, it's very slow. Like trying GPT-5 Pro, which has a noticeable performance difference, stuff is taking 20 minutes, and it's very async in CLI, but Cloud Code has a hybrid mode. So, planning with Opus or Sonnet 4.5 and then doing a lot of coding with a fast model, I'm pretty excited for it. But performance wise on numbers, it's pretty good. I find it like, where is this chart? I find it interesting that, GPT-5 high still doesn't compare to Haiku 4.5 on coding, which we mentioned verified. Like the codex specific model, sure, but like, yeah, Anthropic is doing good with coding.
Yeah, for sure. That is a really nice result, actually.
So it seems good. It seems fast. Swix tweeted this somewhere. He basically tweeted speed is AGI. But otherwise, I don't know. It's nice to have it out. Eugene Yan was asking about this the other day. He still has Haiku in production for speed and cost. And he's like, none of the open source models fill the gap. They don't have tail end reliability. So he was looking forward to this. Interesting to see people still use Haiku 3.5. But okay, I think I can stop sharing unless anyone else has fun stuff. I guess there's a system card. ASL2 model page docs. Oh, system card is loading. Nothing crazy here, but I'm sure someone will dig into this, see what other fun stuff they did. But not the paper for today. This week we have 3 papers with a volunteer, so I'm gonna pass it off. Swix is speaking right now. He is at a Cloudflare conference, so he's literally on stage at this minute. So we're good to start whenever I've got the recording going. You want to do a quick intro?
Yeah. Just want to make sure my mic is working.
Yep, you're good.
Cool.
And your screen share too.
Awesome. So yeah, I'm Rob. I moved to San Francisco about a year ago. Started a startup. It died. Used to work at Google as a machine learning engineer, and I've just been kind of deep diving some RLVR papers. And this is I wanted to present 3, but I realized I didn't understand them super well, so I slimmed it down to just the one that I really got nailed down. I think it's a quite nice and elegant paper, and yeah, I'm gonna talk about that.
And we have slides.
Yeah,
Very nice, very nice.
Cool. Yeah, so feel free to interrupt me whenever. Happy to, go slow, chat, whatever, answer questions. So first I'm going to go through just like a basic high-level overview of reinforcement learning from verified rewards. That probably, if you don't know it, then not a lot of stuff is going to make sense. And then I'll dive into specifically the Darling paper from Meta. All right. So yeah, to just hype up RLVR for a sec. First, a quote from Rich Sutton. An AI system can create and maintain knowledge only to the extent that it can verify the knowledge itself. So this is an interesting take. Rich Sutton, who's not even really that much of a LLM guy, and I think he made this quote more than 20 years ago, but a bit, saw some of the future. RLVR, it was the sort of key unlock that OpenAI, that enabled OpenAI to have their O1 series, where the model would, instead of just instantly sort of spitting out an answer, token at a time, it allowed kind of this thinking process where it will generate a lot of internal tokens and then give a high quality answer. it enabled recently gold medal performance in both this collegiate programming contest, ICPC, other kind of high school math competitions. I think it did almost top performance. And an RLVR is like a key tool for training like agentic tool use. Yeah. Is there, I don't know if there's like a chat I can see if anyone's
There's Zoom
chatting.
chat. Not much yet. Someone was asking if
Okay.
you can share slides, but I think once we get
Oh,
into the meat of it,
and so
you can
yeah,
share
so
later.
should I just share the link to the slides rather, like you don't see my slides itself?
No, we see them. We see them. We see them.
Okay,
Someone was
yeah,
just asking where you can download them later.
Oh yeah. I just put it in. Sorry, I put it in the main latent space Discord chat.
Perfect. If you guys don't know who Rich Sutton is, there's this paper, The Bitter Lesson, that everyone likes to cite. You should read it. Recently, he came back on the DrGRPO podcast, and he's been having some hot takes. Like, these LLMs are not going to do AGI. They don't actively learn. There's some interesting takes this one.
Yeah, and actually, if you even look at that code and think about it a sec, right, it's saying the verifiers are important, but the deployed language models don't have verifiers, right? Like we use them during training, but at inference time, the verifiers are gone. So, Rich might object still to the current state of the art because of this, right? They only use verifiers during training, and so at inference, they still might be lying to you or misleading themselves or misleading you.
It's an interesting take with how deep verifiers go, right? Like we've got very fuzzy verifiers too now, right? Like all the hype is on rubrics as better LLM as a judge, and you're abstracting away a strict definition of verifiers or verification, right? Like I mean, a lot of labs are trying to do reasoning without verification. How can we strip away as much of the verification as we need? And then you've also got this, like you're only as good as you can verify. So interesting little divergence that we're taking.
Yeah. So, well, what is the verifier? It's a function that, given a prompt and a response, tells you true, like the response was correct. So it's very clean and binary. For sort of some math problems where you just want an exact answer, you can sort of force the model to say like, oh, here's my answer after it's done all its thinking. For code, you can, like, if you're just wanting to implement a function or something, you can run the unit tests for that function and see if it passes them all. You can do other clever things, like I think OpenAI has a benchmark called WebBench or something, where they got interesting information from like the web and then generated like true-false questions from that data. So they use the web as a way of generating sort of complicated questions, and then they just throw away some details, and then have, like, you're encouraged, or you encourage the LLM agent, whatever, to use a web browser and try to figure it out. And yeah, there's just lots of different ways you can sort of fit interesting problems into this verified rewards kind of domain. So this also should be kind of review for reinforcement learning versus pre-training. But when you're pre-training, for any given prefix, you have, what's the next token? So you have a lot of dense reward, and it's not really like hackable. You can't really cheat that too well. But since it's teacher forced, the model like isn't sort of recursively generating from its own output. So it's really kind of stays on the rails, but and it's kind of efficient for just ingesting large amounts of information. But unlike reinforcement learning, it's not learning from its own outputs or its own mistakes. So RLHF, which was very big and important about 3 years ago to kind of unlock usable chatbots, trains a separate reward model that doesn't say yes or no, or this is absolutely good or this is absolutely bad, but tries to encode human preferences. So you still have a dense reward, right? It can sort of judge partial answers, but it's kind of easy to hack this reward. You can just look for kind of exploits in the reward model, and I think in the original RLHF paper, when they don't kind of keep the model close to the original pre-trained model, it starts just like spamming words like amazing and beautiful and generous, and doesn't even generate coherent sentences. It just spams out these kind of nice adjectives, and the model likes it. Reinforcement learning from verified rewards doesn't have this problem where you can kind of hack the model, because you actually have to really generate a single or like a specific token that says, or whatever sequence of tokens that say you really nailed the problem. So you've got a clean reward signal, but now you only get feedback once you've done your entire generation, right? So the reward signal is quite sparse.
What's his name? If you guys know Shto Douglas, he works at Anthropic. He says he's scaling RL. He's one of the guys that's heavily scaling reinforcement learning in every domain. He's giving a talk this week, and one of his quotes is RLHF is fake RL. So he had like a little skit about how RLHF is fake RL. Someone in the chat is asking if you can elaborate on reward hackability. I think it's pretty important to understand what that is in RL. Do you wanna take a crack
Yeah.
at
I
it?
mean, you can also take a shot at this, but so when you're doing RLHF, basically you'll train a sort of separate reward model. So you'll say collect, I don't know, 1,000 prompts or 10,000 prompts, get pairs of answers from your model, and then send those pairs to humans. Humans will say, for this prompt, I liked the one on the right better. For this one, I like the one on the left better. So you get this this kind of training set of pairs of responses to a given prompt, and then you learn a model that tries to encode like what would a human, what would they prefer, right? And so you have a kind of a model that can tell you, given two responses, which one is better, but you don't have tons and tons of data for this, and that reward model itself might have like maybe misaligned preferences or bugs or make mistakes. And so as you train your model, your sort of main chat model, to generate responses that the reward model likes, increasingly as you train it more and more, or as you let it go further and further from the base model, you stop getting the real signal, like response A is better than B. For real, like humans would agree with that, and you start picking up on just kind of whatever's weird or errors in that reward model. So you kind of this is called reward hacking, and this is like a big problem with using models to judge the reward.
Yeah, there was this concept of RLAIF. So you have like another model judge the output of another one, and it's not always like reward hacking just really like leads to you add random stuff and then reward goes up because the models disagree. But sometimes it's like it's hard to model your high level preference to little changes, right? So some examples are like emojis, right? Some of the models got really overexcited with emojis. Like basically anything you'd ask them, it would respond with emojis, fire emojis, happy faces. And it learned that through RL because that optimized the mathematical like RL reward policy that, okay, in some domains, like emojis are good, or M dashes. Like let's always add M dashes. And then same thing with some stuff like significancy, right? You want better outputs that seem like they agree with you, but then you take it too far and now the model just agrees with you in every sense and it doesn't push back. So like there's clearly like a trade-off balance, and it's really hard to get that mixture right. But those are like some of the nuanced real examples of reward hacking, right? Like it's starting to realize like, okay, you like how I chat, but I can get a little better reward by throwing some emojis in there. And then that like throws the whole thing off balance. So now you're asking it about like explain a math formula and you've got a bunch of emojis, right? So it can be subtle and it can also be like very, very obvious. Like, you just start shitting out longer responses and you get more rewards because that's what the policy is like saying. And you found out this trick, right? Let me just add noise because long response is good, or the opposite. Let me be really short because short response is good. So those are some examples that are like easier to understand, right? Where you could understand how in some cases that's like giving a good reward signal because it's good for some senses, but then it kind of throws the whole thing off. And reward hacking is where the model like really fits in on, okay, this is giving me a lot of reward. Let me start doing this a lot more, but you might not want it.
Yeah, and another sort of interesting problem with reward modeling is like this problem of Syncopancy, right? Where people tend to like responses that agree with them, maybe even if they're not true. So this can slip into your reward model and then also slip into your chatbot, right? So if you sort of have vaguely equivalent prompts, but one that leans on expecting the answer to go a certain way, models sometimes pick up on that too much. It's another like important problem with RLHF and reward hacking.
Last year in the end of April, OpenAI, actually no, this year, what am I talking about? In April, they had to roll back a version of GPT-4o. They put out a good blog post, I just shared it. Basically, they're like, yeah, GPT-4o, we did a little change and it's loving to agree with people. Not what we want, we got to roll it back. So that was like the first, big lab, like, okay, here's a present issue that we're gonna have to deal with.
Yeah, and I'm sure it's like, this is one where they really screwed it up so badly that they had to roll back a model, but I think it's something that you kind of always have to fight with when you're using these reward models. I'm going to kind of move on. I think that's good. So about a year ago, DeepSeek released R3, and I think, or it was R1, I forget the names of it, but it was a very high quality open source model. And they also released a paper where they described this group relative policy optimization, which has become, I think, a bedrock of work in the research world and the open source AI world. So what it did was basically replace that reward model with like simple verifiers, right? So this only works in domains where you have verifiers, but you've given a prompt, you generate a bunch of responses, you score them with the verifiers, and then you say, the reward is just some like a sum of your scores from your verifiers, and then you say every token in the response that is good is kind of sort of shares that reward, and every token in responses that are bad gets penalized. So it's a very kind of broad brush, but it's a clean signal, and this I think allowed them to get quite close to the quality of OpenAI's thinking models at the time it was released, and became just this basis for a lot of additional work because it worked well. And then one interesting problem people found with these verified reward or GRPO trained models, right, is though it helped improve the quality of the responses, especially if you're going to get just a single response. It actually hurt the diversity of the generations. Like it's kind of compressed the response space on what it could find as the kind of the good answer or a good answer, but it maybe hacked away interesting and useful bits of the model. So if we look at this this plot here, it's from a different paper. you see the base model is this Quinn 2.57B model. And then there's that model trained with GRPO through more and more steps. And on the x-axis is the number of samples you generate. And then on the y-axis is so-called pass at k. So does any, if any of those k, let's say in this 256 like x-axis, you're going to generate 256 responses. Do any of them pass the verifier, right? And we could see that as the GRPO training goes on and on, right? The pass at 1 gets better and better, but as the k increases here up to 256, by the time you get here, the base model actually is maybe doing a little bit better than the untrained model, right? So empirically, maybe one way to say this is you're kind of getting rid of or suppressing some of the model's kind of true intelligence in some way, right? Like it's, yeah, I don't know, maybe I should slow down here or people can ask questions, but I think this is a very kind of important idea to understand.
Is it
right here.
suppressing or is it channeling?
Sorry, say that again.
Is it suppressing or is it channeling?
Channeling. Yeah, I mean, I'm not sure. What would the difference be?
So let's say a base model is super creative,
Yeah.
and then RLHF, RLVR model is less creative but more capable.
Yeah. I think that's a fair characterization.
Yeah, I mean, these terms get tricky, but yeah.
Yeah. Yeah. Could I explain this exactly? Okay, yeah. So I'll sort of slow down and try to say this again in maybe a different way. Or like we'll just try to slowly explain this graph. So what we're going to do is we have one prompt, or we'll actually maybe we'll say we'll have 10 prompts, right? And then for each of those prompts, we're going to generate, let's say, 256 answers, right? If any of those responses are like pass the verifier, right? Then you get credit for covering or passing at 256. So you can be right simply 1 out of 256 times for a given prompt, and that will give you a point there, right? So if you in 7 out of those 10 prompts, you'll have 7 times 256 answers for a given prompt. Just imagine ORing, right? Say false, 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 true, false, false, false. If that OR, right, if there's any true, you get credit per prompt, right? That's how you make this plot. And yeah, empirically, what people have found in RLVR is, right, as you continue to train, when k is small, you have a big advantage. You do much better than your base model. But as you generate just tons and tons of responses, right, you're actually less likely to solve kind of maybe really hard problems or problems that require like some maybe clever spark of inspiration or some kind of weird way of solving the problem, right? So the training process is kind of smoothing out or getting rid of these kind of rough edges that don't tend to work, but at the cost of some diversity or creativity in the models. There are similar findings for RLHF in terms of like I think like just diversity of responses, right? If you ask
那这个题不容易啊。
Okay. All right, I think I'm going to move on here. I think I've got this explained basically as well as I can, but having other people take a shot at explaining this would be worthwhile if it's not clear. So yeah, this is the paper that really motivated this talk. Jointly reinforcing diversity and quality in language model generations. Came out of Meta, mostly out of Meta. I think one of the authors is at Johns Hopkins. And this is just like a beautiful slide that explains the process quite well. So, okay, this may be not a verified reward kind of problem, right? Write a story about a programmer with superpowers. These blue rollouts are considered identical and good. And this green rollout is considered good, right? It's actually a story about superpowers. And it's different than the blue ones, which are considered kind of the same. And then this red one is just doesn't pass the verifier, right? So we want to penalize the red one in both GRPO and in Darling, right? So that advantage is kind of negative off to the left. Whereas both the blue and green ones have advantage that's positive, kind of to the right. But what Darling says is since this green response is different than the blue responses, and it doesn't have any other similar responses, we're going to upweight it. All right, so the advantage, the kind of reward, the score that we assign to this green one is we're gonna say it's more important or better than the blue ones, even though they all pass the verifier, just because it's distinct. GRPO doesn't have any mechanism like this. It only uses the verifier, and your score is independent of how different or any kind of diversity measure from the other responses. Oh, can I make this slide bigger? Oh, I should have went into presentation mode. I'm sorry. I don't actually give many presentations. So I'm full screen. Is there
Next to slideshow.
right here? If I just click this.
The big button. There you go.
Okay.
Wow, it's huge. I will say, just for people to have more background information, the original GRPO was like very vanilla, right? You output stuff, you pick whatever passes the bar, and you average out multiple if they do. But there have been a lot of iterations on GRPO, right? Some of them change the KL divergence penalty. Some of them, there's 3 or 4 different papers we've done in Paper Club. Kimi K2 did a different instance. The original GRPO came out before DeepSeek R1. DeepSeek put out DeepSeek Math in February or so of 2024. That had a slightly different GRPO policy. But the base premise is always the same, right? You generate a bunch of outputs and you have rollouts per se, and then you want some way to give preference towards something. Now, it's known that you lose diversity in responses, so this is specifically tackling that, but there are other variations as well.
Yeah. I mean, I think there's been a ton of work on improving GRPO, and the nice thing about them doing so well and open sourcing it, I think, is that it spurred a bunch of research.
Yeah. So for example, this one is focusing on diversity, right? You cluster outputs and you add more weight to the unique cluster, right? The one that only has one sample, that will promote diversity. Some of the other stuff they've done is they have budget controls for output length, right? So you can give more reward at different lengths, stuff like that, right? And then you can, so that's just another example of stuff that you could prefer, right? You don't want simple questions to have really long rollouts. You'll basically do a similar thing where if an answer is shorter, you give it more reward, or if it's longer for certain domains. So there's stuff like that.
And then here's, just a restatement of that slide to emphasize the difference, right? We have their input prompts, they go through the verifier. In GRPO, we do reward aggregation, and then we use actually kind of the same algorithm that is used for RLHF to do the updating once we've got the rewards. For Darling, we take the inputs, we generate our rollouts. Now we apply our diversity classifier, and we rewrite our reward to prefer answers that are both correct and different than other correct responses. And then we do the PPO update. So it's not really that much a change on GRPO. It just really focuses on boosting answers that are both correct and different than other correct answers.
How is this? Sorry to interrupt. How is this different from? I read a paper called as GRPO done, right? Or I think it's abbreviated as a DrGRPO.
I think I don't know DrGRPO that well, but I think this, like DrGRPO does some calculation that changes like how much reward you get based on the length of the response or something. Like it's
okay.
It changes the reward aggregation, but it doesn't do anything that like compares responses against each other for their semantic content and then reward like ones that are different, right? So I think DrGRPO is like a smaller change to GRPO than this. Doesn't require any other classifiers or anything like that.
Yeah, got it. Thanks.
Okay. So yeah, what does the paper do? Well, they open source their code, which I love. They show that you can use this learned classifier to do this reward reweighting, and I'll show you some results later. But they like promoting diversity actually seems to get rid of this problem of for large K, like lots of rollouts, losing your like this kind of base model intelligence or creativity. So I hope you guys can see this and see the graphs, but the general gist is the base model is green. Here it's a similar plot to the one that I showed a few slides ago, but this is actually from the paper. And yeah, so the number of rollouts is on this x-axis. Your pass at K is on the y-axis. And we see this kind of same trend for the green, like the base model versus the orange model is GRPO versus where as K increases, kind of the base model tends to catch up to, or I guess in some cases even pass the GRPO trained model. But Darling, this idea that rewards diversity tends to keep this edge over GRPO and over the base model, even at large K. So we can, at least in this math domain, maybe see that it's really attacking this problem and giving benefits even most of the time for pass at 1, right? Which is maybe what you care about the most, right? Because this is what you'll tend to ship to users, right? You only generate one response. Yeah. Okay. Here's a question of like, how do they train this math equivalence classifier, right? So the problem it solves is given 2 rollouts, tries to maybe vaguely quickly determine, are they saying essentially the same thing, right? Not string match, but are they solving the problem in the same way? So the way they did this was they tried to get a bunch of like a diverse solution set for different problems by generating rollouts from, I think there's like 5 or 6 different models. I think they're mostly from the Coin family, some from Llama. And then given pairs of those responses, they ask Llama 70B to be like this oracle that generates the right answer. And then they take these pairs of responses with the answer, or with the answer from Llama, and they train a classifier on top of a coin embedding model to be able to mimic Llama, mimic what this big Llama model does. And they got pretty good accuracy, I guess 89% on holdout set. Here's the prompt that they use to generate the training data for this equivalence classifier, which I don't know, seems pretty well thought out and well reasoned, but it's not actually that long. So, right. So how does the mechanics of this work? Right. When you're doing your rollouts, I think in the paper or in the code, they said only 8 rollouts. They'll actually call this this embedding-based classifier on every pair of inputs. And then if any pair, if for any pair the classifier says yes, those answers get merged. And then after you do this, basically, you'll have a partitioning of those responses, right? So if A matches with B and B matches with C, even if A doesn't match with C, you still consider A and C equivalent. And then you form this diversity score that's just like a simple function of the size of the partition, which just says like how many other correct responses are you distinct from, right? So if your cluster is big, you kind of lose some credit because you know, the model tended to like to generate that style of answer. Whereas if you got the answer correct and you were distinct from all of the other responses, you'll get substantially higher reward. So maybe in some sense, it's trying to reward or upweight these kind of more creative or weird or subtle kind of reasoning paths to keep that diversity in the model. Yeah, note that this is like super, super simple, right? We do these n-squared classifications, and then we just binarize the score from the classifier and then form clusters, right? So we kind of do quite a bit of work and then just get very kind of simple outputs to change the reward using that. Yeah, and then this is the actual math. Basically, this Darling score is a reweighting of these base, you know, reward scores from the verifiers with some normalization. They tried some other ways of incorporating the diversity score using addition rather than multiplication. They found that this multiplicative score works the best. And then, yeah, as that previous slide showed, right? Once you're done with this, now you've got your reward scores calculated, and it's identical to GRPO from here. Yeah. So what did I like about the paper, right? So it's a well-motivated problem. I think this approach is pretty simple, right? It's maybe not as simple as like DrGRPO, which just, as far as I understand, like changes some like length normalization, right? You have to introduce this new classifier. But I think fundamentally, if you're going to attack diversity, you need to be able to, you know, compare responses and the semantic quality content of responses against each other. So it's sort of some necessary complexity, has, you know, good results, and they open source the code. what don't I like? So I actually tried to run the code, and then you quickly hit this problem where they don't actually include this semantic classifier for you, so you can't just out of the box run it. Maybe this diversity calculation's overly simple, right? You could imagine maybe you have 4 responses and A is equivalent to B is equivalent to C, and then just, D is equivalent to B, but not to A and C, right? So you've got this little cluster or this big cluster, and then just one little spoke coming out, connecting them. Now the calculation will say D is exactly equivalent to A, B, and C, even though like this graph structure kind of makes you think probably D is a little bit different than A, B, and C. So maybe you should actually give D more credit than A, B, and C. The paper only talks about using one particular diversity classifier for the math problems. They didn't say, see what happens if they were to train that classifier for longer on more data or use like a simpler model. And they also don't actually say how much time is going into doing this diversity classification, right? Could be the case that if you were to spend that time, just generating more rollouts, maybe you would have done better, right? But yeah, all in all, I was pretty happy with how this paper was written, the idea, how to attack the problem.
I will say it's pretty fun exercise. There's like 7 or 8 different like easy to implement GRPO papers that don't share their code and really open source it, but like the models are really good at converting this stuff to code. So like it's one thing to take a paper that doesn't have an open source implementation and like code it up from scratch, but GRPO is one of those things that's actually very easy because they spend a very long section of this paper, of like all the papers, explaining the changes to math, right? Like, okay, we're getting rid of this like normalization distribution. We're doing these little changes. And then, you go into Claude Code or whatever you want to use, and you get a base GRPO implementation. You share the changes, and then you just have it kind of implement it, write tests. And like, they're pretty good at this because you not only have math formulas, you also have like 2 pages of here's why and what's changing and how it changes. And it's a little hard math, at least for me to follow, like, and implement myself in code. It would take a lot longer, but like the models are pretty good at this stuff. So if any of you guys are going through like the Nano GPT, Nano Chats or whatever, and you want to like do some RL training from scratch, implementing GRPO with like a coding copilot and iterations of it really helps you understand what's going on. And it's a lot easier than it seems. But like, quite irrelevant to the paper.
Yeah.
Sorry.
No, it's cool. I mean, I kind of want to get my hands dirty, like, hacking on this stuff. So yeah, maybe I should try to pull out some other papers and, not get stunted by, this big missing piece of the papers is not there. Yeah, this is the end of my talk. Happy to answer more questions.
Very nice slides, by the way.
Yeah, thanks.
And thank you for offering to present.
Yeah, I mean, I initially wanted to present 3 and then realized that was a lot of work, and I didn't like really understand the details of the other 2 papers super well. So I punted and only did the one that, I feel like I really wrapped my head around.
Awesome. Okay, any other questions, comments from anyone?
I have a question about like the open-ended nature of task verification for, let's say, LLMs, and the fact that that's what's led to not having good verifiers. Like, what's the state of the art in terms of like developing closed tasks of some kind and benchmarking them and using them as like a harder type of verifier?
Yeah, I don't know this stuff super well. Yeah, I know Karpathy has this tweet like 3 months ago that says like, everyone should try to be coding up verifiers for their problems, and this would, really help the models.
If you guys have seen the current meme trend of everyone starting an RL environments company. That's kind of what this is, right? Everyone's starting up companies to sell to the labs and make environments. I'll give you a bit of the background of what it's really like. The labs want exclusivity, right? They want their environment, like your unique environment, to be just for them. So you can be the Mercor, that's like you're the player and you can do stuff for everyone. Or if you're a small startup, you're basically a little consulting arm creating little interactive environments for one lab. And then it's like a whole thing to manage to do multiple unique ones, and then they don't want you to work with other ones. But on the other side, a lot of the pilots and where they start is actually you're making environments for evals. So say you're working with not a lab doing RL, you're working or you're working with like a company that wants to do RL or test their agent or whatever. What you're really doing is you're making like a sandbox environment that should test whatever they want to test in like a unique setting. And then they're really just using it for evals. Even though the conversation's like, oh, I want to do RL this, that, it kind of always starts with I want evals for my thing, and we'll help you create unique evals, right? Like it's a eval as a service game. So instead of you can run on Sweebench, how about even instead of like running on real GitHub, how about we make you a sandbox of like random shit coming in through a Slack like chatbot and this whole end to end, and you can see where your agent fails. But I low-key forgot the question you were asking where I started this yap. What's the state of the art of like
Yeah, exactly.
making yeah. So a lot of the companies that are trying to make environments and stuff, they're going at it from that angle, or they're all trying to just sell to a lab, which is cool too. Outside of that, like, not many people outside of the labs are doing the real RL yet. So it's interesting that it covers both domains, right? Um, but that's kind of where it is. And then it's very, very saturated. Like you want RL environments, we'll send you a list of 20 that'll build you a sandbox that tries to mimic your thing. But there's still value in evals for it, right? It's stuff that your thing has probably never seen.
Yeah, it seems like one approach would have just been like hopefully RL just scaled all the way to some sort of all-encompassing God model. But short of that, we'll take RL for task specific. Just max out each task domain basically.
I think RL is very general, right? It scales out as a God model. That's what all the thinking models are, right? Like O1, O3, GPT-5, Cloud Thinking, those are very good general purpose reasoning models. They're not per se trained to just one thing. Now, on the other end, if you look at scaling laws and generalization of this stuff, it just so happens that when you do this type of RL on math and coding, it actually generalizes. Like look at a chess benchmark. We're not doing RL on chess, but you RL on math and code, your chess gets really good. It's just that general rollout of chain of thought step by step. And it's not to say that there aren't issues, right? Like right now we can't do a lot of parallel RL because you have to stay on policy, right? So
Yeah.
the pre-training side is very parallelized. But RL post-training per se, we don't know how to do it that well in parallel across a bunch of, like I can't just optimize parallel RL. Then there's other stuff like diffusion. I can't diffuse RL. I can't do native voice spectrogram RL. So there's stuff there.
Sure. No,
And I guess maybe my chess example isn't good, yikes, but the topic still, the premise still holds. Like there is generalization in RL.
yeah,
AlphaZero was a specific model on chess, but you can RL on just math, and you can see that it generalizes to other domains. There's like quite a few papers on this. There's a lot of small models where they show RL just on the data set mixture. Like I think even the mixed role models, the phi models, they explain what their data set is, and there's definitely a few that are just all math and code, and then you run the benchmark on regular GSM 8K and stuff like that, and it still goes up. So it does generalize. It's also just that that's the most verifiable data right now.
Yeah, that's fair. And I think what I was thinking about was like the AlphaGo debut and like that novel move that happened as a result of just RL maxing all the way till it invented a new move. That's we haven't seen that level of RL maxing on like the other areas, right? So
Yeah. Move 37. You should look
Move
into it.
37.
Pretty fun stuff.
like it'd be interesting. What is the move 37 of like triage my inbox or something? You know, we'll see how that happens.
Some people are using it for proofs. Christian Sigeti is doing a new math Inc. company trying to solve math. I guess the move 37 for interesting stuff is like periodic labs from Liam. They're doing it for RL for material sciences. Predict new materials, silicon and stuff, all on mid-trained RL models, and hopefully you find something cool. Harmonic, I don't know what that is, but there's people doing it in different domains. It's just different problems.
I think it reflects back on the hard versus soft verifiers, and like the RBio that we did last week is sort of related as well. This idea of like what's hard verifier versus soft, and yeah.
Cool. More comments, questions, thoughts? Okay, if not, we can always give people some time back on their Wednesday. Next week.
I see
Yeah, go
one
ahead.
from Freyas of what exactly is mid-training. Does anybody have a good succinct description of that?
Yikes, you do. Yikes knows what mid-training is.
I was gonna, yeah, I don't have a good succinct one. Normally I would assume it's essentially the RL process, right? Where it's if post-training is going to be the chat or instruction tune, and then pre-training is going to be the foundation, then mid-training, I guess, should come before the instruction or chat tune. So I am wrong.
Yeah. My understanding of mid-training is like you're selecting really high quality documents for pre-training. So, you'll first pre-train on like just everything, and then you'll select, I don't know, the top 1% or 10% or something of like really good documents, and finish your pre-training there.
Oh,
And
interesting.
then, yeah. So there's just interesting problems of like figuring out, what's the real good data, and
Like, that and so we have pre-training, we have initial pre-training, then we have mid-training with a refined data set, then we have chat or instruction tune with a different data set, and then we have RL on top of that, which is building the chain of thought to be more rewardy. One wonders like how many other junctures there are to do different stuff. Presumably that can extend the principle in some way or another.
Yeah, typically the mid-training stage isn't like, it's very odd to just say mid-training for general use, right? Because yeah, after you do your trillions of tokens of pre-training, you do save the best for last. But when you think of it like in a specific domain, right? Like say periodic for RL for material sciences, they'll take a base model like trained from scratch and preferably not SFT'd. Then they themselves, like they'll license a bunch of data in different domains like material sciences, books, articles, patents, like as many domain specific tokens as they can. Do mid training where you take like a base Quen model, you domain adapt it towards your domain of material sciences, and you have how many ever high quality tokens. Then they'll do a SFT, RL, whatever. So that's kind of the mid training phase. In general purpose models, it's more so like, okay, here's basic tool use, here's code, here's whatever use cases we find interesting. Let's start training in on those, then do our SFT and RL as well.
Because I remember the thing that's coming to mind is the like the Galactica model, and then maybe like slightly Bloomberg GBT, where they have the general idea was like, okay, we need a new foundation model because we want to do domain specific stuff. And the issue that they were running into was that the domain specific jargon like needed its own tokenizer effectively. So I'm curious as to, because Galactica is kind of old news at this point. So I'm curious if we got to, hey, what we should actually do is not really worry about the tokenizer stuff, and we should just take like a pretty, a capable generalized model, then train it so that it's more capable in this domain. And I'm curious. I want like Galactica plus bench, I guess, to see if Galactica and Fire are the ones that come to mind, I think.
Yeah, that's basically like a good example. Actually, the Bloomberg GPT, that it's not necessarily mid training because that thing was so undertrained, but towards the end of it, they did train on a bunch of unique Bloomberg data set stuff. I think we actually did a paper club. I covered it on Bloomberg GPT, so it should be recorded. That paper was basically all just data set. But then they're like, we have hundreds of billions of tokens of financial data sets, news, filings, press, Bloomberg stuff, and the order in which they do it is pretty interesting. I think you get a lot more conceptual understanding of mid-training by reading small language model papers. So we've gone through a lot of those because a big component is basically their training mixture and the order in which they do training. So just find any of the new small models and then look at their training stuff.
So was Bloomberg GPT effectively like mid-trained with the Bloomberg stuff? Because I feel like they said that they had a new foundation model, right? Or so are they mid-training it and then calling it a new foundation model, or is they actually like, okay, we handpicked all these tokens and now we're just rolling it from scratch? I don't
I
remember.
think the problem with considering Bloomberg GPT mid-training is that half the data set was financial. Like I can pull it up, but I quite strongly remember that half that data set for pre-training as well. Like it was a very clear split. Half of it was like Pile C4 books or something. The other half was 40% financial news. So, it was just a pre-train with a lot of financial.
Yeah, and I think Galactica's the same way, where it's like, we mess with the tokenizer, we, decided to do the data set this way, and then train the whole thing. So I'm interested. That's an interesting, like, there's a lot of decisions that you could make there that didn't really occur to me as like decisions that you could really make architecturally, or like ones that people don't often take. I'm curious if it's just like not effective, or if it's mid-training is kind of the better way to do that.
Regarding the nomenclature, mid-training seems pretty similar to continued pre-training. Like, what's the difference? Yeah.
There's
Or is it
I'll quote Jeremy Howard on the Latent Space podcast. There's no concept of post-training. It's all just training, right? Like at some level, like post-training is still training, RL is still training. It's all just training. It's just that the bound that we define is like quality of data, right? You typically consider like chat instruction following a separate category because the data is per se instruction following, right? And it's like chat user assistant pairs, but you're not doing anything different. You're just training. You're still doing typically SFT, right?
The words go in the magic sand, and that's what it is.
In some, actually, like in a pure literal sense, it is still training. There's pre-training, post-training is the same. The useful bounds difference is that the majority of your 15 trillion tokens will be just random token, understand the world English. The reason we call it post-training is not because you're doing any fancy training. It's just because that's where you're starting to do instruction following and user assisted chat. So there's a bound in terms of what what we're trying to accomplish, but in the literal sense, it's all just training, right? We're not changing the training objective. We're just predicting tokens, right? So
yeah, the way I look at it is pre-training is mostly unsupervised, right? Like including continued pre-training or mid-training. The data might be changing for domain adaptation, but post-training, you're adding in some supervised element or reinforcement element, not completely unsupervised. Yeah.
fair ways to look at it.
Yeah. And I'm curious, like, do you see any companies or use cases where RL is seeping into agentic workflows? I almost see it as one way to squeeze, most of the foundation models. Yeah, I'm curious if you have any interesting use cases that you came across.
Yeah, a lot of the labs have done cool RL for specific stuff, right? Like deep research is RL on OpenAI's model. There's coding ones that have come out. We've shared quite a few in Discord, but there are cool use cases of people doing RL for a task and that turning straight into product. Yeah.
Yeah.
Okay, guys. Thanks again, Rob, for sharing. We're kind of at that time. Next week, we have real-time detection of hallucinations. You can find it in Discord. I shared it in the link here, but thank you for sharing. Really good slides, good presentation.